Hi, my name is Bogdan Pasca. I work for Intel in the Programmable Solutions Group, and my main expertise is designing efficient arithmetic operators for FPGAs. In this talk, I will give a quick overview of the short paper entitled Efficient Modular Multiplication Implementation. The results presented here are joint work with my colleague and co-author, Martin Langhammer. So let's get started. Modular multiplication is a key primitive used in cryptographic systems such as RSA. It is defined as the reduction of the unsigned product AB by the modulo M as shown here. A, B, and M are k bits wide, are unsigned, and for security purposes the most significant bit of M is 1. There are two main classes of algorithms for performing this operation. The first is due to Montgomery and the other is due to Barrett's. In this work, we focus on Barrett's algorithm and propose a variation that, under certain conditions, can reduce resource utilization. Barrett's algorithm performs the modular reduction by first subtracting an approximate number of m's out of AB. This is often referred to as a coarse reduction. Then, since the output T produced during the coarse reduction may still be larger than the modulus M, an additional subtraction may be required to obtain the final result. This final subtraction can be thought of as a simple correction step. The initial guess of how many times M fits into AB is obtained by multiplying AB by the reciprocal of the modulus M, as shown here, and then truncating this result. Barrett's algorithm involves three wide multiplications, shown highlighted here. For the 1000-bit sizes of operands required by current cryptographic primitives, the three multipliers will have a high impact on the resource utilization when implementing this algorithm in an FPGA. In contrast, in this work we propose a truncated multiplier for computing the guess E tilde. With this less accurate guess, the coarse reduction will return a value t, which may be a number of multiples of m of the final result. Consequently, in this work, we propose a fine reduction circuitry which is only marginally more costly than the original subtraction and multiplexer-based one. Additionally, we proposed using an MSB truncated multiplier for the term E tilde m, but note that this may also be applied on the original algorithm as this multiplier does not introduce any error. The architecture of the Karatsuba-based LSB and MSB truncated multipliers are depicted here. We use these multipliers in order to reduce resources, but understand that using the LSB truncated multiplier will also introduce an additional error that needs to be handled in the correction step. The proposed circuitry for this fine-grained correction is depicted here. In a nutshell, it operates by analyzing some top bits of T, the outputs of the coarse-grained reduction, and tries to estimate the number of times M fits in T. This value is underestimated by construction, and a final subtraction stage is required. This table presents the results for A. A regular multiplier implementation, B. An LSB truncated multiplier, C. An MSB truncated multiplier for the same multiplication size. Architectures D and E correspond to the original subtraction and multiplexer-based fine reduction and our proposed fine reduction circuitry. As we propose the replacement of three components in the original architecture, two multipliers and a reduction circuitry, the test whether our proposed solution outperforms the existing one is shown here. By plugging in the ALM numbers from the table, we can see that our proposed solution saves approximately 29,000 ALMs, which is approximately 10% of the original implementation size. This concludes this short presentation. Please see our paper for more details. Thank you for your attention.